funded by Tree Fund. With that, I would like to introduce my co-moderator, Heath Hupke, who's the Grants and Development Coordinator at Tree Fund, to provide us a few updates on this webinar. Heath, the floor is yours.
Well, thank you again for all those across the world joining us today. It's exciting to have our kickoff for our 2025 Tree Fund webinar series. Very excited for today. We want to thank our sponsors for helping support Tree Fund and making this webinar free for all of you to attend. Many of you I know will be seeking some CEUs, so we're very happy to be able to provide these free for all across the world. A little bit more about kind of what also our Tree Fund webinar series is that we are celebrating 10 years in 2025, which is amazing to think about. When we started this, I wasn't here, but we started with about 60 participants, and now we in a few seconds will surpass over 700 people attending already today in the first minute of today for this. So it's amazing to see the progress, both I think technology, but also the impact that we at Tree Fund are able to do. A part of our mission with Tree Fund is to get the information, the dissemination of research and information to everyone, and to make it as accessible as possible. And so that's one way we're able to do that through these free webinar series. We know that this is great information, and want to make sure that anybody that should know about it can know about it. So if you haven't already, I pause on your welcoming, letting us know where you're from. If you can spend the next few minutes letting us know, helping us as Tree Fund know how or where we can be making sure that future webinar series are found. I know a lot of us are on the Tree Fund newsletters or get our emails, or you're on ISA or maybe your local chapter. But if there's other ways that you know about that we can get our information, our Tree Fund webinars to others, we ask that you put that in our chat, and we'll compile all that information to get that out, because we really want to make sure that we are getting this to the most people that are possible. And that's one way that you're able to help us with that information. And again, a little bit more about Tree Fund. We are a nonprofit or a non-government organization located in the United States, but we do partner with international partners such as Canadian Tree Fund, and then we do have grants internationally, as you'll notice today. So thank you for those that have supported us through donations, and including last month or in December, we had a challenge. We had a $500 matching challenge during our last webinar, and we were asking first-time donors if you could donate $25. That would make a world of a difference, and we had a matching challenge for that. And Paul, our CEO and president, put up a $500 matching challenge, and we were overwhelmed and completely thankful. Paul definitely gives his thanks for first-time donors and all that donated during that time. But we were able to raise almost $2,000 through that matching grant challenge. So thank you for supporting us by being here today, by supporting whether you were part of our first webinar 10 years ago, or if this is your first one today. Thank you for being here. Thank you for supporting us, supporting Tree Fund in this way. A little information regarding CEUs. You do not need to put your CEU information, your credentials, your ISA credentials in chat. We don't need that in chat. It was all we got it all when you registered. So you do not need to put any of that in the chat throughout the time. If you are needing a certificate of attendance, please send an email to education@treefund.org during this or afterwards. And then once I get all the information, you'll be able to receive that certificate. It does take a few weeks. It can take up to a few weeks, and including for ISA, we will submit all of your information on behalf of you, but it could take 4 to 6 weeks for ISA to get all of that information processed. And then lastly, for a tree fund upcoming webinar series, our next webinar series, registration is available. If you haven't, you're welcome to register today. It's going to be Tuesday, April 8th at noon Central Standard Time in the United States. And that is going to be long-term effects of electrical right-of-way vegetation management on floral and faunal communities. This is through the State Game Lands Project with Penn State and Dr. Carolyn Mahan. Very exciting. I'm sure many of us have heard from her before, and every year they are discovering more and more information that can be relevant and very fascinating. So welcome you all to attend that, and you can register for that today. And then you can also see that in May, Tuesday, May 6th, we also have another webinar, Enhancing Collaboration Amongst Urban Forest Stakeholders. So welcome you to join that. We will, if you continuously check our website, you will see more and more webinars throughout the year popping up. Next, I would like and am honored to welcome Mr. John Wilson with the Canadian Tree Fund. John is currently entrusted with responsibilities related to treasure and fundraising with Canadian Tree Fund. He's been with them for 25 years, so a little longer than our webinar series. He is a forestry technology graduate of Lakehead University and a horticulture graduate from University of Guelph. John is a retired ISA certified arborist with 30 plus years working with campus services and business operations at York University in Toronto, Canada. He is a passionate golfer, cyclist, and tireless tree advocate. John, the floor is yours.
Well, thank you very much. It's a real pleasure to represent the Canadian Tree Fund, and the partnership that we have with the Tree Fund over years is a commendable relationship, and it's a real privilege to be here to talk a little bit about Jack Hemmel and to introduce our most recent recipient of the Jack Hemmel grant. So to begin with, a little bit about Jack Hemmel. Jack Hemmel, like Highland Johns and John Dooling, who have grants named after them, was a pioneer of our industry. His devotion to what we now know as the ISA mission started back in 1956 and spanned almost 5 decades and concluded when he passed away in 2002, which happened to be the same year that EAB crossed over into the Canadian border. Over his time, he has held many responsible positions. He is one of the founders and the first executive director of what was called the Canadian chapter for the International Shade Tree Conference, which has evolved into 5 separate chapters, 5 of the 30 plus chapters of ISA around the world. In 1970, he was one of 2 Ontario arborists to be entrusted with the position of president of what is ISA today. He's the recipient of many awards, including the Award of Merit, ISA's highest level of distinction. And probably most relevant to this webinar, he was the person with the vision to create a national charity in Canada dedicated to promoting the benefits of trees and the need for professional tree care through tree research and education, which is now what we call the Canadian Tree Fund, that has been going strong since 1995, and last year reached its $1 million fundraising milestone. So Jack was a quality individual, a great leader, a great mentor, and very deserving of having his name associated with this grant. So I would like to introduce our most recent recipient of the grant that started back in 2010. Dr. Guan is a professor at Flounders University and the chief investigator of the National Centre for Groundwater Research and Training in Australia. Now, with 20 years of research experience in ecohydrology and hydrometeorology, his interests most focus on water resource and environmental issues from the interface of land surface and atmosphere through soil and vegetation to groundwater table. He has published over 130 peer review articles with an H index of 37 in Scopus and 41 in Google Scholar. These research activities contribute to United Nations Sustainable Development Goals, number 15, Life on Land, number 11, Sustainable Cities, number 13, Climate Actions, number 6, Clean Water, and number 2, Zero Hunger. His talk today is entitled Characterizing Root Zone and Plant Integrated Hydraulic Systems Based on Above Ground Measures. Dr. Guan, the floor is yours, and thank you very much for your work in this wonderful project.
Yeah, thank you, John. I feel very, well, coincident, my PhD supervisor actually also named John Wilson. He's in Socorro in New Mexico. So yeah, okay.
Yeah, there's a few of us around the world.
Yeah, okay. Okay, I'll now share my screen.
Dr. Guan, while you share your screen, I just remind everybody out there, if you have questions during his presentations, please put those in the Q&A box, and we'll be monitoring that and answering questions with whatever time we have left at the end of the webinar. Thank you.
Okay, can you see my screen now?
Looks great.
Yes?
Yes, that looks good.
Okay, great. Well, thank you, John and Heath and Bob. Yeah, great for your introduction. And yeah, this my title is a bit lengthy, but I promise all the slides, well, most of the slides, very few text, little text. Okay. So here is I'm from Adelaide, south of Australia. So you can see the right-hand side is the city. It's very small CBD, only 1 square miles. And the CBD actually is surrounded by 500 meters wide parkland. So it's surrounding the whole cities. So there are, well, in the metropolitan area, there's many trees in this area. So I try to talk about something about oh, sorry, I try to move the back, okay. About the tree functions, how or benefit from street trees or trees in urban parks. So this is, many of you are already very familiar with this, but I like to point out something about this thermal image, right? So this small community park has a tree actually surrounding this the area, the park, and then in the middle, as a northern section is irrigated, southern section is not. So in these particular summer days, you can see these the southern section is 55 degrees, but the part of lawn has been irrigated only 35 degrees. And when you move to trees, 25 degrees, then we know that because the tree is transpire and also is probably 20 meters above ground, so it's cooler. And then here, so it's this red line delineate the canopy edge. So this part actually is not canopy anymore. So actually it's a shade area. So tree also provide shade, then make the surface cooler than even cooler than the irrigate lawn. So we also did some research to see actually how, sorry, how I cannot make it move. Okay, good. How much cooling that street tree can produce. So we did measurement on these mature white cedar trees. And then it turns out that in summer, these trees use water similar to a person in Adelaide. So a bit less, but about 200 liters per day. And that, because the tree transpire, right? That when it transpire, absorb the heat from environment, so that means it provide cooling to the environment. And that cooling is equivalent to we run these evaporative cooler unit for 12 hours. And yeah, so, and these, if you run this one, it costs you, right? Because you use electricity, use water. But for this system, naturally, is free water, free energy. So it's very good. And other things that we all know that tree provide other ecosystem service. Now, this is one tree just in my neighborhood where I live. So the tree is the canopy, even larger than the house. You look at the car. So I think these types of trees must absorb a fair amount of CO2 from the atmosphere, and it also provide habitat for birds. You can see here. And that is in the residential area. These two trees in a market street, very, very crowded, a lot of people there. And these two trees, I just noticed a couple days ago, about thousands very small birds just perch there in this time of the day. Well, it's in the late afternoon. And the street tree also provide a aesthetic view for people to walk around and yeah. So, but sometimes, and we see street tree dies. So this photo just is I find it from the internet. It's what happened is the tree died in last year in the drought in Perth, Western Australia. And look at these tree died, but surrounding tree are okay. Right? You can see that. And then these tree died in my neighborhood. It's a younger tree, so you can understand. But these mature tree, why it dies? So it's a question, right? So what we can do is perhaps if we have a better understanding of how tree use water may help us to understand why this tree died, but other tree, well, it's okay during that drought. So now we look at the tree, how tree actually use water or uptake water from the soil. So you look at that, it fundamentally is nothing much, well, not much different from we see water flow in a stream. So water flow in the stream is, in this case, is flow along the sort of elevation gradient, right? So gravitational force drive water flow. So here, tree actually is similar, but along another gradient. So you look at this here, a gravitational force still there. That drive water movement from canopy to the soil, but that doesn't happen, right? So actually, in these types of system, we call it soil, plant, and atmosphere continuum. In this type of system, and we have another gradient, it's called water potential gradient. It's sort of energy potential, and we just call it water potential. And then you can see this has a gradient is opposite to this, and then larger than this, the gradient driven by gravitational force. So you can see here, minus 10 bar, we use unit as a pressure unit for this water potential, the quantity. And in this hypothetical case, soil water potential minus 10 bar, minus 14 in the root, and minus 15 in the stem, and minus 25 in the leaves. So you can see this gradient, and that dry water movement from soil all the way to the canopy. Now, you may notice that the value we use here is negative. It's because the water in this system is not free water. It's water attached to a media, like in soil, attached to the soil, right? So you cannot, you take the soil out, the water doesn't flow out. You cut the twig, water does not flow out because it's all what we call it unsaturated condition. So it's all negative value. But that's okay. Minus 10, well, negative 10, larger than negative 14, right? So you can still see this water potential gradient that drive water flow in this system. Now, you compare this system to human body, and we have something, liquid flow in our body. That is the blood, right? So the human heart actually produce about 0.2 bars that pressure difference that can drive blood flow through our body already. But these soil plant system, they need to be work much harder. So they need to have a lot of bigger difference. So from about 15 bar difference can drive water flow in this system. And why? Is it because the conduit that water moves through in this system is what we call xylem. It's very small. It's only order of tens micron. So in a very small conduit, then water flow through must overcome a large friction. So that's why we need large water potential gradient. So next, I'd like to talk about some measurement technique. So many of you already familiar with these, right? So like, for example, you want to measure leaf water potential, and we can use the pressure chamber. So, and to make it, well, the principle of this device is actually quite simple. And we already know that leaf water potential, right, is a negative, right? Certain bar, like negative 25 bars. And when we cut the leaf from the trees, and water, the atmospheric pressure, it push water into the tissue. And we put that twig in this pressure chamber and then apply positive pressure to balance that negative water potential. And once you see the sap coming out, and that pressure is actually balance the leaf water potential. So you can estimate leaf water potential from that balanced pressure, but just negative, right? So that's why we have water potential. Actually, we use the same unit as pressure. Now, another device equipment we use to measure soil water potential. And similarly, we use balance concept, equilibrium concept. Is soil, we take the soil sample, put it into the chamber, and then close the chamber. And then the soil water potential, and then the air in the chamber will build up the equilibrium condition. So once that equilibrium is established, and we measure air dew point, then we can estimate soil water potential. So similarly, we can apply this equilibrium, this sort of principle, and then we use these types of equipment, right? And we can attach the equipment to this stem, remove the bark, and put into the sapwood, and you can measure these, what we call stem water potential continuously. Yeah, it's better than previous pressure chamber, right? Pressure chamber, you need to cut the leaf and then measure just once. But here, you can measure real-time water potential continuously. So next, I'd like to show you some example. So this example, we measure from a tree native in Australia called dripping she oak. So, and here you can see this water potential. We measure using that device, stem psychrometer, and we measure it. And there's multiple trees, tree 1, tree 2, tree 3, and then, so you can see clearly that stem water potential decrease because it's dried, it's drying out. But once there's a rain, and it responds, particularly here, right? So when it's rain, the stem water potential become less negative, then water condition become better. So this is very sensitive. You can hear another one. And then that during the dry interval, the stem water potential decrease, right? So you can look at that in many cases like that. And you zoom into this small section. Now you can see these in 1 day, it changed, right? It's from like minus 2.7 and can decrease to negative 3.3, something like that. So you can see this diurnal change. So why there's this diurnal change is because water, actually the tree lose water is passively, is related to another process called photosynthesis. So the tree like this, when it's in the daytime, and there's a solar radiation, the tree start to do photosynthesis, right? So if you zoom into one leaf, and not even one leaf, zoom into one stomate, and you can see that in the daytime, stomate open, and then CO2 diffuse into the leaf, so that leaf can grab that CO2 to do this reaction, right? Photoreaction, and then to fix biomass. And in the meantime, for the same stomate, there's a different gradient, a concentrating gradient. That's water vapor. So water vapor is moving out of the leaf, or in this case, one stomate, and that process we call it transpiration. So you can see this process is passive, right? So in the nighttime, now that there's no solar radiation, most of tree species or vegetation species, they don't do photosynthesis. That means they don't need CO2. Then they close stomate. And in that case, we stop this transpiration. So with that, we now can understand this. Also, I use this diagram to explain. So in the daytime, leaf open stomata, many stomate, right? Stomata, and that transpiration happening reduce the water potential. I use water level sort of to demonstrate that, but actually it's water potential decrease. You decrease water potential, water flow start from stem into the leaf. And when that happens, stem water potential also decrease, right? And then that dry water flow from soil to stem. So that's why you see outer sunrise, so it start to decrease. So that, look at this daytime case, okay? Now, what about in the nighttime? In the nighttime, leaf close stomata, and now the water potential recover slowly, right? Overnight, then it can very likely can reach the equilibrium. So again, you see that we come to that equilibrium concept. So once the system get to equilibrium, then you measure any part of this system, you can get soil water potential. So usually that happen in pre-dawn. So that's why people measure pre-dawn leaf water potential. Now we use this device, we can estimate pre-dawn stem water potential so that to find out how much water actually stored in the root zone soil. Okay, and so these situations very likely happen in this pre-dawn condition. And now I look at another thing is we just talk about this water potential, and we know that soil water flow from soil to canopy, right? And driven by these water potential gradients. And then a different part of this flux, we have different names. Like here we call it root water uptake. Here we call it sapflow. And then when you get to canopy, we call it transpiration. So average over a day, they probably similar. The quantity are similar. So this sapflow, actually, we can measure it more robustly and for a long time using a sapflow meter. So this is just one example of heat ratio method sapflow meter. And very simple, well, principle also simple. It releases the heat, and then by measure, there's a thermistor to measure response of temperature. If there's no sapflow, then the response of upstream and downstream will be the same, but sensor will be the same, right, at the same time. But when it's sapflow, and then there will be difference. But so by measure this difference response, and then we can estimate sapflow. So there's a two measurement, what we call above ground measurement, stem water potential I mentioned earlier, and now sapflow. So earlier where I talked about that in pre-dawn, then the hydraulic equilibrium can be established, right? But that sometimes it doesn't happen. So I'll show you with this sapflow, you can see this very clearly. So this is a sapflow of a tree, or 3 trees, the same species. And at the beginning, right, at nighttime, sapflow is 0. So that means the equilibrium established, because when the equilibrium, no sapflow, right, no water movement. So it's 0, so it's good. And then by after a while, you can see that there's a nighttime, this sapflow does not come back to 0. It means overnight, in this case, it's not, the hydraulic equilibrium has not been established. And these, particularly in the street, one factor may be because of the street light, right? But also because of there's not enough water in the root zone, so that it take longer time for tree to get to the equilibrium, hydraulic equilibrium condition. Okay, even that, we can still use this measurement to find out root zone moisture condition. So here I show you example. So in this case, see, this is an all nighttime sapflow, and I plot in the horizontal axis, right? So this nighttime sapflow never get to the zero, right? And then I plot this sapflow with this water potential, because we simultaneously measure them together, right? So we can plot in this. But when we fit this line, and then find out the intercept along this zero sapflow, so that although the real system has not reached equilibrium, but we can extrapolate this to get to the hypothetical equilibrium condition, and that condition can tell you root zone water potential, or how much water available in the root, right? Or water condition in the root zone. Okay, now I'd like to show you two different situations. One is normal situation, one is drought condition. Let's start with, again, from this conceptual diagram. So in normal condition, we just talked about that, right? In the daytime, we have this gradient, and that gradient drive this water movement from stem, from soil to stem, from stem to leaf. And what about in drought condition? Under drought condition, now all these still three components there, and then water potential in each component is smaller, lower, right? And you can, in some situation, you can still maintain the same gradient, but you could measure the sapflow, you can see that the water flow, the size, the amount of water flow now from one component to another becomes smaller. Why? You gradient the same, it becomes smaller, then something else change. So that change is the capacity of this xylem to convey water, that capacity decrease, and that we call it hydraulic conductivity. So that also tell, well, it means in the drought condition, xylem may lose some of the hydraulic conductivity, right? So I now show you the some data. So these data, again, simultaneous above ground measurement. So water potential, stem water potential, and then sapflow. And these in the growing season, in summertime, in this summer usually is humid, and but sometimes they have a summer drought. So these in the plantation side, a small plantation side, and then these the brown line show is daily sapflow. Okay, so you can see again here this diurnal fluctuation of water potential. You will assume this nighttime represent root zone water potential, and then this is minimum is daytime, right? Minimum water potential. This difference actually sort of show you the gradient, right? From soil and to stem. So you look at the gradient. So earlier, a gradient is large, and then you have sapflow large, right? Later, gradients slowly decrease because of there's no rain over about 40 days, no rain. So it decreased, and then sapflow decrease. So it's sort of understandable because you now have a small gradient. But you see here, this gradient keep the same for some time. But why sapflow keep decreasing? Because hydraulic conductivity now is keep losing hydraulic conductivity. Yeah. So once you have rainfall or you have irrigation, so water potential can return back, and then after this it return back. So now we compare this part and to that part because it seems to be the gradient are similar, right? Nighttime, pre-dawn, and daytime, this difference similar to that, but the sapflow is a lot smaller, just a quarter of earlier situation. So that means you already lose have lost probably 3/4 of hydroconductivity. Yeah. Okay, so now I try to explain a bit more about this. So earlier we talked about this water flow through these trees through xylem, right? And that's a xylem is composed of all different these sort of xylem vessels. They connect together, and some xylem is bigger, and some is smaller, right? When the tree or under drought condition, and some xylem may become water in the xylem may become discontinuous. For example, here, a dry condition for some time, this xylem vessel water is all gone. So it's become, now this vessel is filled with water vapor. So when that happens, the water from here, what we call upstream, and then at downstream, it cannot connect it. So in this case, this xylem unit is become malfunction. It does not convey water anymore. So if this situation lasts longer, and then air can penetrate into this. So when that happens, it's very difficult for this xylem to repair itself. So if just water vapor, maybe you irrigate it or out of rainfall, it can slowly recover. Okay, there is sort of a microscopic view of this xylem, what we call it cavitation, right, happen in these. Now, why this important? Because this can explain why in the drought condition, some tree die, some not. So now I show you one example. For those from the Southwest United States, and you are familiar with two species, right? One is pinon, one is juniper. So before I show you this drought response, I'd like to look at the some conceptual diagram and about these loss of conductivity, what we talk during the drought condition, right? So and these we call it hydraulic vulnerability curve. That's a term. And these show you is explain this. The horizontal axis is xylem pressure, has a unit. See these pressure unit, but now we use megapascal. So 1 megapascal equal to 10 bar, roughly. Yeah. Well, it probably exactly 10 bar. Yeah. So it's 0 means very good water condition, very good in this xylem. So more you become more and more negative, then xylem become drier and drier. And you see these two species, pinon and juniper. And the open symbol is pinon. And then we just focus on this one is the root xylem. And that one solid symbol is root xylem of juniper. So you can see pinon actually easily to lose the hydroconductivity. And there's one quantity called precise 50 is the xylem water potential at which the 50% of conductivity loss, right? So that we call it precise 50. For these pinon, it's about minus 2.7 megapascal. Then root xylem lose 50% of hydroconductivity. Now for juniper, it can go down to minus 5.6 megapascal. Okay, so keep that in mind. Now we look at this real case. So these photo taken in Arizona in I think in early 2000 for multiple years drought, and then these pinon juniper woodland have mortality. But you zoom into it, look at detail, and then actually this is another site in New Mexico. You can see in this case, as the majority of dead trees is coming from one species, that's pinon. And for juniper, actually survive in this drought. And the reason it survived in this drought relate to that vulnerability curve, because you see, pinon, right, is easy to lose hydroconductivity. The pinon want to protect this hydraulic pathway, so that stomatal actually close. See here, that's a stomatal conductance. If 0 means stomatal close. So when leaf water potential decrease minus 2 megapascal, it closes the matter to protect hydraulic pathway. So don't leave it lead to a loss of hydroconductivity, right? When it closes, then will impact another process, it's photosynthesis. So that's like a human. So if the tree close the matter, it stop photosynthesis. Like a human, we stop eating. So in that situation, when you have disease attack you, then you cannot, easy to be knocked down, right? So in this case, I think the interpretation of why pinon die in this drought because of the bark beetle attack this pinon, and while pinon does not have enough energy to attack, to protect itself because it stopped photosynthesis. So all relate together, right? Relate to this hydraulic vulnerability curve. So now I move back to this the death of these street trees. So again, these species die, but surrounding is okay. So why? So I think if we have more understanding of this system, it will help us to prevent something like that, right? We can take actions. So I list some concept here. One thing we will talk about the hydraulic vulnerability curve, right? So another one is we call it maximum hydraulic conductivity. It just say how much the capacity of these xylem to convey water under the optimal water condition. So it show you the efficiency of the hydraulic efficiency of the trees. And another one is Luzhong water storage capacity. It's just a look at this tree. How big of this Luzhong? How much water it can store in the wet season or in the previous rain? So that type of knowledge would be very useful, but it's very difficult to find out because it's underground, right? And then at any given time, what's the Luzhong available water, right? If we know that, we know whether we need to take action. So I skip last one because it's because I want to save time. Now, here come to my idea is talk on the title, so using above ground measurement to look at the whole system, like soil plant system or Luzhong, integrated Luzhong plant system, the property and also condition. The above ground measurement, I mean sapflow and water potential, the two concurrent measurements. And then these system, these idea like a periscope, like a periscope in a submarine. So use a periscope to look at the surface condition while submarine is still underwater. So here is we go opposite, right? So we don't know anything about, or we don't know much thing about underground Luzhong, but we can measure above ground condition, and then we can see, well, the underground situation. So that's the idea. So now I'll show you some experimental site. Actually, this site is funded by Tree Fund. And this is the community park. I'll show you some instrumentation here at the site. So we have in this site, we have above ground measurement. Sorry, I have above ground measurement, water potential and sapflow. And then we also have on ground measurement. That is the geophysics method, measure electrical rigidity. And then we have below ground measurement, measure water content at 3 depths. So we actually drill a hole and then bury sensor in this hole. And when we auger the soil, we see little roots. So we don't know whether this point is quite close to the tree already, right? We don't know whether that measurement is representative to the whole Luzhong, but that's what we can do. So here show you some result about that. This is to show you the different times of cross section, shallow soil, just 1 meter at different time, of electrical conductivity. So the higher means likely more water. So you can see here in November, in spring, out of the whole, the end of spring, out of the whole spring, soil is quite dry. And then, but just in early December, there's some rain. So you can see now there's some water, right? And then that lasts some time, and then dry out like that. So it's very good, provide you an image. And then these are 2 trees that we have equipment to measure about ground measurement. And but even these, you see the change, but you don't know how big of root zone, what exactly the soil moisture there, right? It just gives you quality view, not quantitatively. And now I show you this is stem water potential. Now this is a gray box, is eucalyptus trees, and the equipment we apply the tree not as good as the other one, that dripping shield. But even that, we still see some good data. And then now I plot predominant water potential from this measurement, right? Against soil volumetric water content measured by the 3 depths, average them, and you see good relationship. So so there's some connection. So you never know which one is more accurate, right? So I would say predominant water potential probably is better because we directly measure the water condition from the tree. So I'll show you why. So now I average 3 depths of water content into these blue lines. And then this yellow line is this predominant water potential. So we just focus on that response to rain. Though that's a 2 rainfall, right? So there's a response for the root zone moisture and quickly dry out. This is surprising because the soil is from 1 meter depth of 30, 60, 90 centimeter, right? Why it dries so quickly? And but our predominant measurement is look like more reasonable. So it's that the whole root zone become replenished with water from this rain. It support water the tree water use for some time. Like similarly for that one, right? Support for some time. So it looked like to me is this stem water potential is better, right? And now I go back to another side. There's a dripping sheol side. The reason we go to that because we have longer data series and multiple trees, more number of trees. Again, based on 2 measurements, water potential and then sapflow. So based on these, now we can derive individual hydraulic xylem vulnerability curve, and then for throughout the season. So different season, they have a different one. And then we plot this one, the maximum hydraulic conductance. So because we work on the whole trees, now we call it conductance. And then we also look at PSI 50. Remember that? These tell you how resilient, or is more negative means the xylem system is more resilient to drought. And maximum hydraulic conductance higher means more efficient to convey water. So we just focus on these from wet season to dry season, right? So the whole root zone and plant system drying out, it loses some hydroconductivity. So maximum hydroconductance decreasing over that. So lose efficiency, but become more resilient, right? You can see even just for a tree, so these vulnerability curve actually change seasonally. So I think this is probably the first time we show these data to show these seasonal, what we call it, plasticity of hydraulic property on that. So now this plot to show, I plot this safety, go this way, safer. And then this one is efficiency, this go opposite, right? Higher efficiency and then lower safety, and then opposite that's for this. And then throughout season, there is a wet season and dry season. You can see these. And these are now we publish for discussion actually in a journal. So for some of you who are interested, please leave comments on that. This is open for all discussion, so everybody can leave a message there to join the discussion. The student also present this in the recent AGU meeting in Washington, DC. And now I briefly talk about now another side. We use the same data to look at now underground situation, the whole root zone. So these just show you the root zone accessible moisture. So how much moisture available in the root zone at any given time, right? So this each one to tell you how much water left there. So when you have rainfall, that root zone water increase, right? When rainfall, root zone water increase. Without rainfall, it's decreasing because the plant keep using the water. So similarly, you can see here, and in this case, this water rainfall does not actually change much of the root zone moisture. Probably just because it's in the dry season. So rain is just wet surface soil, and then does not produce a lot of root zone water replenishment. So again, I skip this one to save time. And this work is still ongoing. We now have just complete the glasshouse experiment, and then the student now preparing the manuscript to look at how we can use above ground measurement to look at the root zone condition and properties. And related to this above ground measurement, we also use another device called thermal radiometer, and to look at the canopy temperature, because we find out that you measure canopy temperature at the right time, at the right condition, and then these we can derive index can very good correlate with the predominant water potential, right? So that means we can just use thermal radiometer, measure this canopy, we can understand a root zone condition. Okay, I nearly finished. So now bear with me. I need to read these. These some of the summary that I have. So first, the water we talk about today. Water move from soil to tree canopy is via xylem, right? What we call it, that hydraulic conduit called xylem, along a water potential gradient. And how much water a tree use at any given time depends on two things. One is hydraulic gradient, or what we call water potential gradient, and xylem hydraulic conductance. And when soil gets drier, the hydraulic conductance decrease, and the water potential gradient may also decrease, and both these decrease lead to a smaller water uptake. And now, in terms of these hydraulic conductivity degrees, we use this plant hydraulic vulnerability curve to describe, right, the hydraulic pathway loss in the well, sorry, that's a type of that loss or loose pathway loss is efficiency. That's okay. They also tell us how safe the hydraulic conduits will be under drought condition. And that is the major part. Is I demonstrate that using concurrent above ground measurement of plant water potential and sapflow, and then you can use it to derive one is plant hydraulic vulnerability curve, and that including both hydraulic efficiency and hydraulic safety parameters. And we can use that to derive root zone water storage condition. Okay, I think that's it, but I need to have two more slides. One is I like to acknowledge many people, particularly the students and my colleagues. So they work with me over the years to develop this idea. And then the reason we can develop this idea also because we have organizations provide funding, right? Like this, the first phase is from National Center for Groundwater Research Training, and that is funded by Australian Research Council and National Water Commission at the time. And then the student, many of these students are funded by China Scholarship Councils. And then recently we have the funding from this group organization, including Tree Fund. And now this project is still going. We have this group of organizations, particularly Hope Innovation, provide funding to keep us working more into this field. And then in the last, I leave this reference I mentioned in this presentation, and most of it from my own group, but also some other colleague studies leave here. And then I also leave my contact information. And yeah, with that, I'll thank you for your attention. Thank you.
Dr. Guan, thank you very much for your presentation. That was it was fascinating, I must admit some of it's over my head. I don't work in so that level of tree physiology that you're working in, but I think it was fascinating to see some of that work. We do have a number of questions, and so I'm going to jump into a few of those real quick. Before I jump into those, just a reminder, this has been recorded. We are going to put this on the Tree Fund website in a few days, and so you can go back and watch it. I'm probably going to have to rewatch it because there's areas that I want to watch a little slower and try to comprehend everything, as I'm not a tree physiologist. But this is really fascinating work. Dr. Guan, there was a great question here. There's a number of questions. I'm going to pick a few, y'all, because we don't have time to get through all of them. But what makes a tree more vulnerable to hydraulic conductivity loss?
What made tree more vulnerable for the loss?
Hydraulic conductivity.
Yeah, I think it's probably related to the size of xylem, I would say. Well, if the xylem conduit, right, is bigger, it's probably more likely to lose the hydraulic conductivity when water potential decrease. Yeah. Yeah.
And
I think it's all trade-off, right? Because if you want to make it more resilient trial, so the xylem need to be smaller. But if xylem is smaller, then it's more difficult to convey water. So you need more energy gradient, right, to drive water flow. So when it's in a wetter condition, these types of species will be more difficult to get water than the species with a bigger xylem. That's I think, but I don't have data to show that because my lab does not measure the size of xylem, so I cannot. That's my understanding. So, yeah.
And closely related to that, there was a question that if there's any equations for the type of tree and size to estimate water uptake, right? There's always a question of how much water the trees use, how much to irrigate. And I'm assuming this question is kind of closely tied to that. Do we have any equations related to specific species?
Okay. Well, the tree use water because of leaf need to do photosynthesis, right? If a tree is a bigger canopy, large canopy, have a lot of leaf, I would say it will use more water, right? So, I mean, for the same species. So because others are similar, now bigger size, of course, use more water. But whether there's an equation to do that, to calculate that, it may be difficult. But in the optimal condition, maybe you can estimate based on like potential evaporation, right? Because all this is constrained by atmospheric demand. Because the reason why we current demand, or we use a term called potential evaporation. So you can use it like you familiar with the reference evaporation, reference ET of the FAO, that organization, and you have these like regular weather station data. You can estimate that. So I would say that would be the first approximation to estimate how much water a tree use, and yeah, use that.
Thank you, Dr. Guan. There's a bunch of other questions, really good questions. I think we're running out of time. My clock is reading we're about a minute to the top of the hour. I apologize that we're going to get to those. We'll share those with Dr. Guan, some of those questions, and he might possibly reach out, but I can't promise that. I just want to remind everybody with CEUs, those are applied automatically. If you registered, you put your name, you give us your CEU. If you need a certificate of attendance, send an email to Heath Hubke at education@treefund.org, and he can help you with that. If you have any other questions about the webinar, that's the email to send. And we want to thank the Canadian Tree Fund with the Jack Kimmel. They sponsored the international research that we saw today and various other projects around the globe on a number of topics. So thank you, John Wilson, for sharing the background with the Canadian Tree Fund and the work you do with the Jack Kimmel International Grant Programs. And then finally, I want to thank our speaker today, Dr. Guan. And thank you for being here. I don't know if everybody realized, but it is very early in the morning in Australia right now. So he got up very, very early to share his research. So thank you very, very much for being on the Tree Fund webinar series with us today. With that, we will see everybody back next month with our next Tree Fund webinar series. And thank you, Dr. Guan.
Okay, thank you.
Thanks all. And as always, thank Heath for putting this webinar series together and getting it advertised. And just real quick, thanks to everybody who sent comments in the chat about how we can better advertise these webinars. That is always important. So thank y'all and see y'all next month. Cheers.